Assalamu alaikum, we hope you all are doing well. Today we are going to talk about an interesting topic of graph theory called graph traversal and two important techniques used for it along with their implementations. These algorithms may sound technical, but they actually power many real world systems that we use every day. In this video, we will first understand what graph traversal is and then explore how BFS and DFS are used in real life applications. Let's get started.
Let's begin by understanding what graph traversal actually means. Imagine you're exploring a city with many roads and intersections. To visit every place efficiently, you need a clear strategy. In computer science, this idea is called graph traversal. Graph traversal is the process of visiting all the nodes or vertices of a graph in a systematic way. Graphs appear in many real-world systems such as maps, social networks, and computer networks. To explore these graphs efficiently, two main techniques are commonly used: breadth first search, also known as BFS, and depth first search, also known as DFS. Let's understand how these two techniques work.
First, let's look at breadth first search or BFS. BFS is a graph traversal algorithm that visits nodes level by level starting from a source node. It first explores all the nearby nodes then moves to the next level. Now let's look at the depth first search or DFS. DFS works differently. It explores as far as possible along one path before backtracking. So in simple terms, BFS explores wide first while DFS explores deep first. Both techniques are powerful and are used in many real world applications.
Let's look at some interesting examples where BFS is applied. Imagine this scenario. You are walking through a city and suddenly feel like having a coffee. You stop and think, where's the nearest cafe? Your phone quickly opens the map and suggests the shortest path to a cafe. But have you ever wondered how your GPS system finds that route so quickly? Behind the scenes, algorithms like BFS help navigation systems analyze the map and locate the best path. In GPS systems, the map is treated as a graph. Locations or intersections are represented as nodes, and roads connecting them are edges. BFS starts from your current location. It first explores all nearby roads and intersections, then gradually moves outward to the next level. By exploring locations step by step, BFS helps find shortest route to your destination efficiently.
Have you ever noticed the people you may know suggestions on the social media? Sometimes it suggests people who are connected to your friends. This is not random. Algorithms like breadth first search help social networks analyze connections and recommend new friends. Social media platforms represent users as nodes and friendships as edges in a social graph. BFS starts from your account. First, it explores your direct friend. Then it moves to the next level and explores friends of your friends. This level by level exploration helps platforms efficiently suggest new people you might know.
Imagine editing a photo and selecting an area of similar color, like using the paint bucket tool. Behind the scenes, algorithms like BFS help the computer identify and group related pixels. In image processing, each pixel can be treated like a node in a graph. BFS starts from one pixel and begins exploring neighboring pixels that are connected or similar. By exploring these pixels step by step, BFS helps detect and group objects or regions in an image. This technique is used in tasks such as image segmentation and flood fill.
Now let's move to the second important traversal technique, depth first search. Unlike BFS, DFS focuses on going deeper into a path before exploring other options. This makes DFS very useful in problems where we need to explore possible solutions deeply before trying alternatives. Let's explore some interesting applications of DFS.
Imagine you are inside a maze trying to find the exit. You choose one path and keep moving forward. If the path leads to a dead end, you go back and try another route. This strategy is exactly how DFS works. DFS starts at the maze entrance and chooses one path to explore. It continues moving deeper along that path. If it reaches a dead end, the algorithm backtracks to the previous point. Then it tries another unexplored path until it eventually finds the exit.
When a computer plays against a human, it must analyze different move possibilities to decide the best move. To do this, it explores many possible game scenarios using DFS. In tic-tac-toe, every possible move can be represented as a branch in a game tree. DFS explores one sequence of moves deeply until the game ends, whether it's a win, lose, or a draw. After reaching the end of that path, it backtracks and analyzes another possible sequence. By checking many possibilities, the algorithm helps the computer choose the best move.
Another important application of DFS appears in task scheduling problems. Sometimes tasks depend upon other tasks. For example, you must compile code before running a program or finish prerequisites before taking advanced courses. DFS helps organize such tasks in the correct order. In topological sorting, DFS visits each node deeply before moving to the next node. When a node finishes processing, it is added to the topological order. This ensures that dependencies are completed first before moving to the next task. This method is widely used in project scheduling, software builds, and dependency management. Now let's explore the Python implementation of BFS. BFS explores a graph level by level. We start from a node, mark it visited, and use a queue to keep track of neighbors to visit next. Each time we remove a node from the queue, visit it, and add all its unvisited neighbors to the queue. This way, we explore nodes closest to the start first. For example, starting at A, BFS visits nodes like this: A, B, C, D, and F. Level by level traversal is perfect for shortest path problems. Now let's look at DFS. DFS goes deep into a graph before backtracking. We start from a node, mark it visited, and then recursively visit each unvisited neighbor. It explores one branch fully before moving to the next. Starting at A, DFS visits nodes like this: A, B, D, F, and C. DFS is great for exploring all paths or solving maze-like problems.
To conclude, graph traversal algorithms help us explore complex network efficiently. Breadth first search works by exploring nodes level by level, making it ideal for tasks like GPS navigation, social network analysis, and image processing. On the other hand, depth first search explores deep path first, which makes it useful for problems like maze solving, game decision making, and task scheduling. These algorithms may seem simple, but they power many technologies that we use every day. Understanding BFS and DFS helps us see how computer science connects directly to the real world systems. Thank you.